Hello and welcome. In this video, we will talk about how to use integrals to calculate volumes of three-dimensional solids. We'll focus on two specific types of solids. The first kind is a solid formed by revolving a two-dimensional region or a two-dimensional area about either a horizontal or a vertical line. Perhaps this is something that you've seen before in Calculus 1, but we'll talk about it again here. The second type of volume that we'll talk about is the volume of a solid that has parallel cross sections that are the same shape. These aren't necessarily rotated volumes, but we can still use integrals to find volumes in this scenario. Before we specifically talk about volume though, let's revisit the idea of a definite integral, and let's maybe think of it in a different light. So remember back to when you first learned about definite integrals. Perhaps you drew a graph something like this. We have some function f of x. We start at x equals a, and we go to x equals b, and we want to find the area under the curve. Well, how do we do this? We start by dividing up the region into smaller subintervals. We used n subintervals, and let's just imagine picking one of these endpoints here. Let's call it x sub I. The width of each of these intervals was delta x. And the height of one of these small regions is the value of the function at x sub I. So we imagine taking a rectangle here that has a width of delta x and a height of f of x sub I. And then we imagine taking these rectangles, finding the areas, and summing up all of the areas of these rectangles from A to B. And we wrote out a sum something like this. We added up the height, that's f of x sub I, times the width, delta x, where I ranges from 1 to n. That's the number of subdivisions that we use. And then if we take the limit as the number of subdivisions goes to infinity, well, that would be taking smaller and smaller widths, so the error involved goes away. So if we take the limit as n goes to infinity, this is the true area under the curve. And that's actually the definition of the definite integral. This, by definition, is the integral from a to b of f of x dx. So this is the origin of definite integrals. This is how we choose to define them. And when we find the value of a definite integral using fundamental theorem of calculus, that's not using the definition, that's using the fundamental theorem. But this is how integrals are defined. As we begin this section, I want to shift the way that we think of an integral. I want to think of an integral as adding up many small slices. And these slices could correspond to area, they could correspond to volume, they could correspond to other physical concepts as well, such as work or pressure or mass, other sorts of things as well. But we want to think of slicing up a region and then adding up those slices using an integral. And if we can find an expression for the area or the volume or whatever of a representative slice, then we can use an integral to find the total area or volume or whatever it is that we're interested in finding. So let's draw a picture and try to think of integrals in this way. Imagine once again that we have this generic function f of x, and again we're trying to integrate from a to b. We're trying to find this area using a definite integral. We know that the integral corresponds to the area, so this expression means the area under the curve. But I want to think now of taking just one representative slice of this area, right here. And instead of calling the width of this slice delta x like we did before when using the Riemann sum, let's say that this is a very thin slice of area, and let's just say that the width is dx, some infinitesimally thin slice of area. Okay, so that's the width. What is the height of this slice? Well, the height is whatever the value of the function is. Let's just call it f of x. So the area of this slice is the height times the width. Well, the height is f of x, and the width is dx. So this expression here, f of x times dx, corresponds to the area of this little slice. Now, how do we find the total area of the entire figure? The way to find the total area is to integrate. And think of the integral here literally as adding up all of the representative slices starting at A and ending at B. Let's take a look at this in Desmos. All right, so here we have some generic looking function. We want to find the area from x equals a to x equals b. The area looks something like that. That's the area under the curve. Now, I want to imagine taking one representative slice of this area. Here's a representative slice. The width of this slice is dx. And in order to find the total area, I will find the area of that slice and then integrate from a to b. And essentially, when I integrate from a to b, what the integral does is takes the slice starting at A and it adds up all these different areas of all these representative slices from A to B. So when we integrate, the limits of integration tell us to start with the slice at A and add up all these areas until we get to B. That's what the limits of integration tell us to do. Now, thinking of integrals in this way is a little bit more hand-wavy, it's a little bit more intuitive, but if we can think about finding representative slices of areas or volumes or what have you, and then adding up those areas or volumes using an integral, that way of thinking of integrals will serve us very well for these applications that we'll take a look at. Now that we have this slightly different way of thinking about integrals, let's take a look at volumes of rotation. Consider taking a region between the function r of x and the x-axis, from x equals a to x equals b, and let's imagine rotating this two-dimensional region around the x-axis. This formula will give us the volume of the resulting solid. But where does this formula come from? How do we come up with this? The pi, the integral of r of x squared? Well, let's take a look at developing this. We won't do this very rigorously, but we'll get an intuitive understanding of why this formula is true. Okay, so let's once again graph this. And we imagine some region. Let's call this the function r of x. Think of r here as corresponding to radius. We use the term r to remind us of a radius. And once again, we're integrating from a to b. But now we're taking this region and we're rotating around the x-axis. So all of this area here is being rotated around the x-axis. How can we find the volume of this resulting solid? It would look something like this. It's hard to draw this in 2 dimensions. I'll show you a better visualization soon. But how do we find this volume? Well, let's imagine taking the volume of a representative slice. So I'm going to think of taking a slice of this region, just a slice of the area right here, and then think of spinning this slice around the x-axis. When I spin that slice of area around the x-axis, I get this little disk. This is often called the disk method for this reason. I get this small, thin disk of volume. Let's say that the width of this disk is a small change in x, dx. And then how do I find the volume of the disk? If I can find an expression for the volume of this representative slice, then I can use an integral to find the total volume. So let's talk about the volume of this slice. Well, this slice can be thought of as a cylinder. It's a cylinder that's on its side, and the width of the cylinder, or I guess the height if you put it on its side, is dx. What is the radius of this cylinder? Well, the radius is whatever the value of the function is. This distance here, from the x-axis to the function, that is the radius. So the radius of this cylinder is really the function r of x. How do I find the volume of a cylinder with a radius r and a height h? Well, in general, the volume is pi times r squared times h. If I have a cylinder with a radius r and a height h, that's the formula. My slice here has a radius of r of x, and the height is really this change in x, this dx. That's the height of this very thin cylinder. So I add a dx, and this expression here, pi times r of x squared times dx, that is the volume of a representative slice. That's the volume of this red figure here. How do I find the total volume? Well, I add up all those volumes by using an integral. So the total volume of this three-dimensional solid is the integral of this representative slice. So volume equals the integral of pi r of x squared dx. and I integrate from a to b. Those limits tell me where to start adding up the representative slices and where to end. Okay, pi is a constant, so we could just take it out front, and we see that we obtained this formula here. Now, this is hard to visualize in 2 dimensions, so let's take a look at a 3-dimensional visualization. Here we have a 2-dimensional plot that's actually in a 3-dimensional graphing system, but just imagine this red curve as some function f of x, and let's imagine taking the area that looks like this and rotating that area around the x-axis. What would this look like if we rotate that area around the x-axis? Well, this solid would look something like this. We have what looks oddly like a lampshade. So if we rotate that 2-dimensional region around the x-axis, we get this solid of revolution, and now we have an integral expression that will allow us to determine the volume of this solid. Let's think about a representative slice here and view what the representative slice would look like in this scenario. Thinking just in 2 dimensions, here is a representative slice of the area under the curve. We will take that representative slice of area and rotate it around the x-axis. When we do so, we get this shape. It's a disk. It's not exactly a cylinder, but we can imagine if we made the width of this smaller and smaller, it would be more and more like a true cylinder. If we take this representative slice and move it through the region from A to B, then we will obtain all of the volume of the resulting solid. As the representative slice moves through the region, the volumes of all of those slices combine together to make the volume of the entire 3-dimensional shape. The integral is taking these representative slices and moving them from A to B to find the total volume of the shape. I hope that you now have a better intuitive understanding of where this volume formula comes from. Let's take a look at how to use this volume formula to solve some problems. Take a look at example 1. Find the volume of the solid formed by rotating this line, y equals 2/3 x, about the x-axis from x equals 0 to 3. Whenever we start one of these volume problems, we first want to sketch the 2-dimensional region to grasp a picture of what this looks like. So let's graph the function y equals 2/3 x. Well, y equals 2/3 x, that's a line passing through the origin with a slope of 2/3. I'm going from x equals 0, this is a, to a equals 3, b equals 3. And my function is f of x equals 2/3 x. When x equals 3, y will equal 2. So my line looks something like this. I will rotate that graph around the x-axis. Now you can imagine what this would look like if we rotate around. If we spin this graph, we will have a cone-shaped solid. All right, so how can we find the volume of this solid? Well, our volume formula is pi times the integral from a to b of the radius squared dx. What is the radius here? The radius is the distance from where I rotate, which is the x-axis, to the outside of this shape. This here is the radius function r of x. And for this example, the radius is just the y value of the function. So for this specific example, the radius is simply the function itself. This won't always be the case, but for this example, the radius is simply the y value of the function. So we can plug that straight into the integral, and we have pi times the integral from 0 to 3 of r of x squared, that's 2/3 x, quantity squared, dx. Let's go ahead and work through this integral quickly. The 2/3 is being squared, but that's a constant. So I'm going to square this to get 4/9 and then take it outside the integral. So pi times 4/9. Once again, 4/9 comes from squaring 2/3 and then taking it out front. And now we're just integrating x squared. That's all that's left. Integrate from 0 to 3, and I have pi times 4/9 times, now I take the antiderivative of x squared, x cubed divided by 3. From 0 to 3, we're using fundamental theorem of calculus now to evaluate this definite integral. We first plug in a 3 and then we plug in a 0. And we have pi times 4 over 9 times 3 cubed over 3 minus 0 cubed over 3. And we can simplify this a little bit further. 3 cubed divided by 3, I can cancel a 3 and get 3 squared. And 3 squared is simply 9. So notice that I have a 9 here in the denominator. That can cancel with the 3 squared up here, and I have pi times 4. That's the final answer. So 4 pi is the volume of this cone. Can we generalize this? Can we imagine taking a cone, but instead of having a specific radius well, in this case, the radius overall would be 2. So our overall radius of the cone is 2. And the height of the cone would be this distance, which is 3. So we really have a cone here with a radius. The radius, yes, would be 2. And then the height is 3. Can we generalize? What if we have just a radius instead of 2? What if we have a radius r and then a height h? Could we generalize? Well, it turns out we can, and it's fairly simple to do so. This is example 2. Example 2, we take r and h to be positive constants, and we find the volume of the solid formed by rotating the graph of r over h times x. This is again just a line with a slope of r over h, but when we integrate from 0 to h, we will have a cone with a radius r and a height h. Let's solve this in general. So once again, we begin by sketching the two-dimensional region. It's a line passing through the origin. This is the function f of x equals r over h times x. We're integrating from 0 to an x value of h. So this would be a sideways cone. And if we think of plugging in h into the function, we would have a y value here of r. So we take this. This is a general cone with a radius r and a height h. We're going to spin it around the x-axis and find the volume. Once again, we use the volume formula pi times the integral from a to b of the radius function squared. The radius function, once again, is just the y value of the function itself. So we have pi times the integral from a to b, and r of x here, the radius, is r over h times x. Now this might look a little bit intimidating because we have the constants r and h and pi, and these a's and b's, these should actually be from 0 to h. So we integrate from 0 to h to obtain the entire volume. But remember that r and h, these are just constants. So when we have r over h here in parentheses, we're going to square those. So we'll have r squared over h squared, but then we can just take that out front. So this integral simplifies to pi times r squared over h squared times the integral from 0 to h of x squared dx. So I took this r over h, squared it, moved it out front. That's how I got the r squared over h squared. Let's continue solving this integral. We need the antiderivative of x squared, which is again x cubed divided by 3. So pi times r squared over h squared times x cubed divided by 3, integrating from 0 to h. We begin by plugging in h. We have h cubed divided by 3 minus 0 cubed divided by 3. 0 cubed divided by 3 is just 0. So we have pi times r squared over h squared times h cubed divided by 3. I can cancel h squared with the h cubed, and I'm just left with an h. So my final answer here is pi r squared h divided by 3. This is the volume formula for a general cone that has a height of h and a radius at the base of r. We just developed this formula using the idea of an integral. This concept of finding volumes using an integral is an incredibly powerful concept, and we will extend these ideas to more and more useful applications.